Thanks, Jyoti. So, all right. So today we're going to be talking about the game of NIM. And this is essentially subtraction on steroids. We are going to have multiple instances of subtraction that we're going to basically be playing in parallel. So this is an old game. Again, I think it's been around. It's one of those things that's been around for ages. But perhaps the actual name NIM was assigned sometime in the early 1900s. And this is how it's played. So essentially, you have multiple heaps or piles of stones, tokens, however you want to think of it. And each of these can be thought of as a subtraction game on its own right. And the way you play NIM is essentially the way we did game disjunctions yesterday, which is to say that a player on their turn has to pick a non-empty heap to work on, and then they can remove any number of tokens that they want from that heap. So this is where it differs slightly from subtraction, because in subtraction, or at least the way we encountered subtraction, the setting was that you have a fixed set of numbers. So we said a subtraction game starts with n tokens. And then we had, the rules were given by a collection of numbers, which told you how many tokens you were allowed to remove on your round. Unlike that, in a game of NIM, once you fixate on the heap that you're going to be working on, you can basically remove any number of tokens from that heap as long as that many tokens are available. So if you're working on a heap which has 5 tokens, you can remove 5, 4, 3, 2, or 1 tokens. If you remove all of them, that heap becomes empty and that's not playable anymore. If you remove less than all of them, then that heap continues to survive for future rounds for the opponent to choose as well. So that's how NIM plays out. Let's look at maybe a quick example. And once again, I'm going to mimic the one in the book. So here is the first pile. It has 1 token or stick. And here's the second one. And here's the third one. So hopefully it's clear that we have 3 groups here. And the first player takes the entire third heap. So that's gone. And we're left with now just 2 groups with 1 and 2 sticks respectively. The second player chooses to pick up 1 stick from here, not both, which brings us to this situation. And here note that although both these heaps are individually winning for the current player, if they were to play these games locally, they would be winning in that universe. But since you're playing the combined game at this point, this is a losing position for the current player, because no matter which heap the current player empties out, the other heap, they're going to be left with 1 heap that they give to the opponent, and they're going to empty that out. And the player that's playing this round, the player that's playing this round is bound to lose. So hopefully that's clear. So it's a smart move for the opponent to only pick up 1 stick from the second pile and not empty it out. Indeed, emptying it out would have been the winning strategy if that was the only game they were playing. But for the sake of the big picture, they actually let that pile survive. And then this is now losing for whoever is playing right here. Okay, so hopefully that makes sense. You could draw out the game tree the same as we have been doing for subtraction. But for any individual pile, the game tree is now going to have as many children as the size of that pile. So remember, for subtraction, if you had a pile like that, you would, depending on what the numbers A, B, or C were, you would typically have 3 children, which would be the result of removing A tokens, B tokens, and C tokens. This is not the case here, since we have 6 tokens altogether, you're always going to see 6 children based on how many you remove. So you could remove all of them to get the 0 pile. You could remove 5 of them to get the 1 pile, 4 of them to remove to get the 2 pile, 3 of them to get the 3 pile. And then you would have to remove just 2 to be left with 4. And you'd have to remove 5 to be left with 1. Of course, there are no passes, so you have to remove at least something, and these are the possible outcomes. And so this is what an individual sub game looks like. It's, like I said, a subtraction variant where you have no restriction on how many tokens you can remove. And the game of NIM can be thought of as a game sum of these extended subtraction games, right? So for instance, with the example that we saw earlier, we had this was the combined game with these sort of 3 groups. And you can think of this as a sum of these extended subtraction games, where the sum is defined essentially as exactly what we said the overall NIM game is. When you take the sum of the individual subtraction games, what's happening is that the player has to choose one of the universes to play in, and then they dig deeper into that in the sense that once they've picked one of the games to play in, that's where they make their move. And the resulting game is going to be that all the other universes stay intact. And the one where the move was made is morphed according to the move that was made. So that's essentially what's happening. And you can once again use outcome classes to sort of label this tree as we have been doing. So you can let the tree play out, and let me just again work through a very small example. So we have, let's work out what we said over here with the 2 piles with 1 stick each. So if you had to draw the game tree for this one, you could either empty out the left pile as the current player. So you'd be left with an empty pile plus a stick in the right pile, or you could empty out the right pile, in which case you 1 stick plus an empty pile. And from here, of course, both of these games end in an empty game. Those are the terminal nodes. And once again, we know that the terminal nodes are losing for the current player or winning for the other player. And as long as you have a red child to move to, the current situation looks good for the current player. But now, because all your children are green, you don't have a red child at this level. The parent node is in fact losing for the current player, which is exactly what we said earlier. So you can basically subject NIM games to the analysis that we saw on the first day. You can draw out the game trees, and all of that works out nicely. One concept that's useful as we go along is the notion of equivalent games. And understand what game states are effectively the same. That's just putting it in informal language. But if you want to actually fine-tune this idea, then here's a possible definition. Okay, so what I want to say is that G and H are equivalent if their outcome classes combined with any other third game are always the same. Okay, so for any third game that you bring into the picture, okay, what we have is the outcome class of G plus J is the same as the outcome class of H plus G. Okay. So that's a bit of a definition. Let's just take a minute to absorb it. The idea is that no matter which game you throw at both of them, no matter which game you combine with G and H, they're going to exhibit the same behavior. So if G plus J, so of course, J is a common game, just keep that in mind. So G plus J is winning for the current player if and only if H plus J is winning for the current player, right? And notice, for example, that any game that is all the games that our other player wins are in this sense equivalent, right? This is something that we saw yesterday. So if you remember, we said, if you have an other player win combined with a current player win, the combined game is a current player win. And if you have two other player wins, then you end up with another player win again, right? So let's take two games which are wins for the which are wins for the other player. So these are P positions. Let's say G and H are both other player wins. These could be terminal nodes. It could also be some node in the middle of the game tree. It could be a more complicated scenario. But we do know that both of these positionally are other player wins. Then think about what happens if you bring in a new game, right? If the new game is a N, right? Then both of these work out to an N. And if the new game that you bring in is a P, then again, both of these work out to being a P, right? So in that sense, all the P positions in any game are equivalent according to this definition. But notice that this, of course, doesn't work the same for the N positions, which is why the definition is still kind of non-trivial and interesting. It doesn't just split the game states into two classes. The P positions are equivalent, the N positions are equivalent. This is not the case because I think just yesterday we have looked at how N plus N could go either way. So we do have examples of scenarios where you could have N plus N working out to being a P and N plus N working out to being a N. So I'm sure, inspired by the examples that we've seen yesterday, you can actually populate this with concrete examples to convince yourself that not all N games are automatically equivalent. Okay. All right, so let me just pause for a second here to see if there are any questions. Apparently not, but do feel free to let me know if anything is not clear at this point. So we did say that today's discussion is going to be about something that we call nimbers. And nimbers are numbers that you associate with nim games. So it's a very natural choice of a name. So our task here is to somehow see if we can associate a number with every game state of nim. So you have a nim game and you want to associate with it a natural number or possibly zero. In fact, in the book, there is a sort of a comment which says that for combinatorial game theorists, like the set of natural numbers always is thought of as being a set that includes the number zero. And now, depending on how deeply entrenched you are in math culture, you might find this anywhere between scandalizing to not a big deal. So I think there are a lot of jokes about whether zero is a natural number or not. But for the purposes of our discussions, I might sometimes forget to be explicit about bringing in zero in this fashion. So the set N of natural numbers is to be understood to contain zero if I forget to be explicit about it. Okay, so that's, I think, the decent compromise. And so what do we want to do? So we want to associate with every game a number which reflects, in some sense, the equivalences of the games, right? So we want to split up these games into classes, and we want to say, well, let's hope that all the games that are equivalent end up getting the same number associated with them. And then hopefully, math people being math people are going to talk about how they can possibly combine these numbers and play around with them. So that will eventually bring us to the notion of nim sums and how those work. But for now, let's just try and find a systematic way to associate numbers with nim games. And the way we're going to do it is as follows. Because we know that all the P positions are equivalent, we're going to start off by saying that if the outcome class of a game is P, and perhaps I have not been, I realize now, the explicit about this notation, but hopefully it was not, hopefully it didn't throw you off. So O of a game state, little o of a game state denotes the outcome class, which is P or N, depending on whether it's an other player win or a current player win. So I think I did warn you about the P and N notation in the first state. And because that's the notation that you're going to be seeing in the book as well. I'm going to stick to that, but I'll often I'll continue to use current player and other player instead of next player and previous player, which is what the letters stand for. Okay, so if the outcome class is P, right, if it's another player win, because we know that all of these games are indeed equivalent, we want to associate a common number with them. And since we haven't assigned any numbers yet, and this is the first one that we're about to assign, a natural number to choose here, no pun intended, is 0. Okay, so then the associated number here is 0. So all the P positions get a 0, right? Okay, so that's a good place to start. Now, what do we do if we're stuck with a position that's not necessarily a P position, it's an N position? So now this at this point is just a definition. What we are going to do is basically say that let's look at the children, right? That's a natural thing to do. So you're somewhere in the game tree. And we're going to build this up bottom to up. Actually, perhaps it's nice to do this with an example. So let's maybe try to work through a small example. So let's say we're doing the subtraction game with 1, 2, 3. Or perhaps we could just say that it's a nim heap since we're talking about associating numbers with nim game states. So let's say we have this nim game, which is just a single pile with 4 sticks. That's going to give us 4 children. So you could either remove 1, remove 2, remove 3, or remove everything. And that's a terminal node, so that's easy. That gets a number of 0 right here. This one has a child, which is 0. So we know this. And we're going to hop over to the parent, and the number that we're going to assign here is, well, it's just stepping up by 1. I don't know if that's a natural way of thinking about it, but the parent of a 0, especially when this is an exclusive child. So the rule is going to be that if 0 is your only child, then you're going to get a 1. That's how we build this up. Remember that we want to be thinking eventually about why these numbers preserve equivalence. And I don't know if you'll have enough time to get to that today, but let me just give you the rules. So here we do know okay, so this is a 0. This is a 0. This is a 1 from what we said previously. So what about 2? Well, we know that 2 is not an N position. So if you remember the way we did okay, let me just draw out the outcome classes as well. From what we have so far, the 0s are losing for the current player. And we know that as long as you have a 0 to go to, you're winning. As long as you have a red child, you're winning. So these are winning. Actually, all of these are sort of trivially winning because it's just one heap and you can remove whatever you want. So maybe that was actually not as interesting as I hoped for it to be. But regardless, what we want to think about here is, so what number should we associate with this game state? We haven't figured that out yet. It does have two children. And I suppose one thing to think about is, is the set of, is the instance that has two heaps, is that morally equivalent to the heap that has, the heap that has two sticks. I don't know what I just said. The heap that has two sticks versus the heap that has just one. Are these heaps equivalent in the sense that, is it true that you can tag on any game to it and, basically be left with the same outcome class? Is this true? Because if that is true, then they should ideally get the same number, because we've been saying that we want to associate numbers in such a way that I did not write this out, but the goal is that games that are equivalent get the same numbers. So let me just call it an ID. So you can think of the notion of equivalence as splitting the game states into a bunch of equivalence classes. And all we are trying to do here is to give labels to these classes, right? Now, what about this question here? Do you think that the game state involving one heap, the game state involving one heap that has one stick and one heap that has two sticks, are these the same? Well, let's see. For instance, we already know that if we do this, then this is losing for the current player. But if we do this, then that's actually winning for the current player, because the current player can transition to a state that is losing for the then current player, right? So please give me a heads up if this makes sense, right? So we have an example of a J such that the outcome classes of these things combined are not the same, right? So the games that we are looking at are not really equivalent. So we should be careful about making sure that this game does not have the number 1 associated with it, because it really is a different game. It's not in the same equivalence class. And what I'm going to do is just be sort of frugal and associate the smallest number that has still not been assigned to an equivalence class, and that's going to be 2. So that's what I'm going to do here. And now if you draw out the tree further, right here, you're going to have trees that you have already seen, so I'm not going to expand on them. But once again, the question is, what is the number that we associate with this guy here? And again, you can convince yourself that this is really a distinct equivalence class from anything we've seen before. And it's going to be the same here. So in this example, it turns out that we're going to again be sort of lazy and pick up the smallest available numbers and associate that with these files. Okay. In general, it turns out that if you're looking at least in a game of NIM, you're in some game state and you have children the numbers associated with them are, let's say, T1, T2, and so on, up to, let's say, TK. Let's say you have K children, and these are the numbers associated with those game states. Then one way to figure out the game state associated with the parent is to take the smallest number that is not in this set. So the smallest number that's missing from this set, the smallest natural number missing in this set. So for instance, if you don't have a 0 as an immediate child, then the number here is going to be a 0. But if you do have, for instance, let's say, let's do a couple of quick examples. So if you have 0, 1, 3, 4, then that's going to be 2. And like I said, if the 0 is missing, then this is going to be 0, and so on and so forth. Now, of course, you could ask yourself, why do we want the max? So this is max is minimum excluded number. That's what it stands for. And again, it's a good exercise to think about, why does the max capture equivalence classes the way we want to? So right now, think of this as a definition of how we want to label the game states. It's a well-defined idea for assigning numbers with game states. And what we want to validate is that it actually respects our original intention, which is that all games that are equivalent should in fact be assigned the same label. Okay. So in terms of why that happens, in particular with the game of NIM, is something that is, I mean, we're going to come back and talk about it. And we're also going to come back and talk about how do we add these numbers, add in quotes. We're going to take NIM sums so that we can combine two numbers to end up with a number. And what's, so what you want to do is to be able to say that I can take two NIM games, G plus H, and now you can take the numbers associated with them and hopefully come up with a meaningful way of adding them, so that the number that you get as a result is actually the number that corresponds to the sum of the two games. That's a natural thing to desire. For some reason, it looks like my screen share is stuck, but okay, it's back on my screen at least. Right, so Ashutosh is asking if the children are never equivalent to the parent. The fact that we are taking the max does mean that we end up with a number that is not assigned to any of the children. And that does seem to imply that, yes, the children are not going to be equivalent to the parent. And I don't know if that makes intuitive sense, because these are all game states that you go into. So with one move, can you generate a state that's exactly the same as before, or is in the same outcome class as before? So, okay, to be honest, I don't have like a super intuitive explanation of this consequence, but that's good food for thought, and hopefully we can come back to it when we meet next. I'm going to, just like yesterday, leave you with a quick thought regarding mirroring. So let's think about, let's say, two games, G and H, which happen to have the same number. So let's say they both have number 4 associated with them. And let's say here 4 was obtained because it was the max of 0, 1, 2, 3. And let's say here 4 was obtained because it was the max of what do you think G plus H is going to be? 4 plus 4. I've given a bit of a hint when I said that this is similar to the mirroring strategy that we talked about last time. Right, so here, G has 4 children, whose numbers are 0, 1, 2, 3. And now H has more. Oops, it doesn't have 4. Of course, that's excluded. Right. So, well, I'm going to think about it from the perspective of the other player, mimicking what the first player does. So let's say the first player picks G and moves to a smaller number. Then the other player can pick H and move to the exact same number, right? Or if the first player picks H and moves to a number that's smaller than 4, then the other player can do the same. Yes? So the other player controls the game in the sense that they always ensure that that after their move is made, so after the current player moves and the opponent moves, the opponent can ensure that the resulting game is still the sum of two games that have the exact same value, right? So that's something you can do if the first player makes a move that's smaller than 4. But what if the first player makes a move that is bigger than 4? Like they go to H and they play 7. What does the other player do here? Well, yes, now the other player is going to move so that you actually end up being 4 in both, right? So you can move, so the game H is now transformed to a situation where, well, you're going to, as the opponent player, you're going to leave G alone and you're going to play in H and you're going to make H work out to 4, right? And this you can always do because you've moved to a game where 7 is the smallest excluded number, which means all the numbers less than 7 are available to you. So in that game, you can pick the moves that takes you to a game whose number is 4, as far as H is concerned, and G stays intact. So you're moved to 4 plus 4, right? So no matter what the first player does, you can always transform the game back to a state where it's the sum of two numbers that are exactly the same. And you can convince yourself from here that you can always take it down to a win. Okay, so a win for the opponent, just to be clear. So these positions, when you're summing two games which have the exact same numbers, are always going to be other player wins. So X plus X is always 0 in the world of number sums. We're going to explore number sums in more detail next time. It has a fun connection with popular binary operation, and if you've not seen it before, I think it's a cool thing to work through. And in the meantime, food for thought is, why does this particular association via the MEX actually make sense in terms of being meaningful labels for equivalence classes? So let's think about that if we have some time between now and when we meet tomorrow. I'm sorry again for going a little bit over time, but we will stop here and see you tomorrow.